Alright. Everybody ready to start a new chapter? Yeah. We're really winding down, okay, because we got chapter 8, chapter 10, 2 sections out of chapter 12. We're all we have left, so kind of slows down when we get to this point. We go a little more in depth on each thing and cover less ideas, okay? Fewer ideas. So, and chapter 8 is also where we hit our first inferential statistics. Okay, so big day in stats class. We're gonna actually get to do some inferential statistics today. All right. So, anybody have any just general questions or anything before we get going? Can't think of anything? Okay. We're kind of few in number today. All right. Okay, so chapter 8, we are doing the same type of process in each section. Okay. Well, 8.2 is kind of a standalone. Okay. 8.1, 8.3, and 8.4 are all the same type of process. And the process is we are estimating some kind of population value. Okay. In 8.1 and in 8.3, we're estimating population means in both of those sections. Okay. So the difference between what we're doing today and what we'll be doing in 8.3 is that today, when we're estimating population means, we're making an assumption. We are assuming that we know the population standard deviation, and that's sigma. We're being a little bit unrealistic today, because usually in real life, if you're estimating the population mean, you don't already know the population standard deviation. There are a few occasions when that can work, but so being a little bit unrealistic today, but we'll get to our adjustments that we need to make in 8.3 later. Okay. But that is a big assumption that we're making for the time being, okay, that we know the population standard deviation. So as far as the problems we're working in this section, we have to be told the population standard deviation. Okay. All right, so our goal is we want to be able to have some sample data, okay, and be able to use that sample data to estimate the mean of some population. Okay. So here we're thinking like we can't do a census for some reason, and there are lots of reasons why we can't do a census, and it's too expensive, it takes too long, all kinds of things going on there. So instead of doing a census, we're just collecting a sample of data and then trying to get an idea about our population mean from our sample. Okay. So to do that estimation, okay, we start with something we call a point estimate. Okay. So a point estimate is just a single value, single number, okay, that we're using as our estimate of whatever type of population parameter we're trying to estimate. In this section, we're just thinking about estimating population means. So we'll have some point estimate that is our single number estimate, or single number guess, if you want to, okay, of the population mean. Okay. All right, so we're going to start with our single number estimate. Okay. When we're choosing the value that we use as our single number estimate, we have to be careful. Okay. What we don't want is we don't want our point estimate to be what we call biased. Okay. We want it to be unbiased. Okay. So we've got another definition here of what we mean by having an unbiased estimator. Okay. That's when we have a point estimate, and our definition says does not consistently underestimate or consistently overestimate the actual population parameter. Okay. So the idea here is we want to be careful that we pick a number to use as our point estimate that's not generally too big or generally too small. Okay. Our goal for it to be unbiased is that we want about half the time our point estimate to be too small, and about half the time our point estimate is too big, okay, if we miss. So it's a big deal, okay, that we want our point estimate to be unbiased. Okay, but we're going to kind of skim over some of the details there. Okay. I'm going to give you a little bit of insight into how we're picking the number we're going to use for our point estimate, okay, because we talked briefly about Chapter 7 last week. Okay, so here we could get really deep into this. We're not. Okay, we're just more interested in coming up with the estimation than the theory behind why it works. Okay, but we talked last time about a sampling distribution of sample means. And we mentioned the central limit theorem. So the idea there really briefly was that we collect out all the possible samples of a certain size, calculate the mean of each one of those samples, and then what does the central limit theorem tell us about this? Again, this is just very brief. Okay? Central limit theorem tells us that the mean of this sampling distribution is going to be the same as the mean of our population. Okay? And that when we just pick a random sample mean, okay, they're going to be spread out, right? All these are sample means in here, all the data under this curve. And if our sample size is big enough, our rule of thumb is our sample size needs to be 30 or bigger, then we know about the shape of this sampling distribution. It doesn't matter what the population looks like. If our sample is big enough, we know the shape of this sampling distribution is going to be symmetric and bell-shaped or really close. Okay, it's going to be symmetric and bell-shaped. So what that means, if it's symmetric, 50% of the time our data is going to be on the left side, 50% of the time our data is going to be on the right side, right? It's symmetric. So that means that if we use a sample mean as our point estimate, it is unbiased, okay, when the central limit theorem is in effect. Okay, because half the time our guess is going to be too big, half the time our guess we get is going to be too small. So a sample mean is unbiased. Okay. There are some other choices we could think about. Again, we're not getting too deep into it, okay, but there are some other choices we could think about for different numbers we could use as our point estimate. We could think about using a median or using a mode or using something else, but we don't have the guarantee with those numbers that we do with a sample mean that it's going to be unbiased, that it's not going to always be too big or always be too small. Okay. So okay, if all that's just a bunch of gibberish, it's okay. All right, here's the big takeaway. If we're trying to estimate a population mean, what number are we going to use as our point estimate? A sample mean. Okay? So anytime we want to estimate a population mean, our point estimate, the number we're going to start with is the mean of some sample data. Okay, sample. Right, that's the big takeaway there. Okay? So let's look at one. Okay? So this says find the best point estimate for the population mean of test scores on a standardized biology final exam. And then on the next slide, we got a simple random sample taken from the population of test scores. Okay. So here, just try to get the big picture of what we're doing in your head. Okay. We have some population data. We've got a bunch of test scores out there. So maybe there's 1 million different biology test scores out there. Okay. We're trying to come up with a way to estimate what the mean of that whole population would be just by knowing these sample values. Okay. We don't want to have to look at all 1 million test scores. Okay. Or maybe there's some reason why we can't. So instead, we're just going to collect a sample. And then the way we're starting our estimate is with a point estimate. And our point estimate here, since we're trying to estimate a population mean, would be the mean of this sample data. And on this one, you could calculate it, add them up, divide by how many we have. But on this one, our point estimate would be 81.6. That's the mean we get when we add all these up and divide by how many we have in our sample. Okay? So this is our number that we're going to start with, our point estimate. We're going to start with when we're trying to estimate the mean of the whole population that we can't see. Okay? That's going to be our starting point. Questions so far? I know we're kind of got off into a little bit of theoretical stuff, but there's the practical stuff. If we want to estimate a population mean, the point estimate we start with is the sample mean. Okay? That's our big takeaway. Okay. So there we go. Here's an estimate for the population mean. It's a point estimate because it's just a single value, but that would be an estimate for the population mean of these test scores. Okay. Well, we've got a problem with that. Okay, that's not going to be good enough. Because if we just pick this value, 81.6, we're saying this is our estimate for the mean of the whole population. So we can't see the whole population. Could be a million test scores somewhere we can't see. Okay. How likely do you think it is this would actually be the mean of the whole population? Not very likely, okay, because I mean, we got all that data out there. Now, what are the odds that this is actually the mean of all that data we can't see? It's very unlikely. Okay? In fact, the probability that that's actually the population mean is pretty much zero. Okay? So the problem with just using a point estimate as our estimate for the population mean is that we're pretty much guaranteed to be wrong, and that this is not going to be the actual number. Okay? But that is our starting point. That's our starting point, our point estimate. So what we need to do, we need to figure out some way to make our estimate more accurate. Okay? So this process is pretty intuitive if you stop and think about it. Okay, so imagine you're with one of your friends, maybe you're out shopping somewhere and you see somebody and your friend says, hey, how old do you think that person is? Okay. Well, if you just throw out some number, if you just say 27, okay, you're probably wrong. Okay, just chances are of all the ages they could be, you're probably wrong if you just throw out a number. But normally that's not how we answer that question. If somebody says, how old do you think that person over there is? What kind of answers, what would you expect to hear as an answer? What do people say? They don't say, I think they're exactly 27. Or they really don't say, I think they're 27 years, 10 months, and 11 days old. We try to kind of hedge our bets. What do? Yeah, like what kind of guess do you?
Like they're in their 20s. They're in their...
Yeah, we're in their 20s, or what'd you say? Yeah, like a range of values, right? You say, I don't know, between 25 and 30, something like that. Okay. That's all we're doing. That's all we're doing. So what we're going to do, instead of just using this point estimate, we're going to expand it to a range of values. Okay? And that range of values gives us more of a chance that the number we're trying to estimate is actually in our estimate. Okay? That's all we're doing here. So the thing that we're making when we do that, okay, when we get a range of values, is called an interval estimate. Okay? So if we just pick one exact number, that's a point estimate. But if we turn that into a range of values, that's called an interval estimate. Okay? Ideally, what we would like to be able to do is if we have an interval estimate, we would like to be able to say how confident we are that the real number is actually in our range of values. So maybe we'd want to say we're 90% confident that we actually have the number in our estimate. Or maybe we want to be more sure, we want to say we're 99% confident. Okay? So what we're going to do is we're going to come up with an interval estimate, and we're going to attach a level of confidence to that. And when we do that, we get this thing we call a confidence interval. Okay? And chapter 8 is all about confidence intervals. That's what we're going to be making in all of chapter 8. Okay, one thing here, if you see just lowercase c, that's the symbol we use for confidence level. Okay. And c, you can write it as a percentage, right? We're such and such percent confident, or it can just be a decimal, like 98% would be 0.98. You can represent that either way. Okay. So that's our goal. And we want to be able to, we're going to start with some point estimate based off of a sample mean. That kind of gives us a guide of where to start our estimate. And then we want to expand that to some range of values. And how we do that, we're going to do that based on how confident we want to be that we have the real number in there, okay, to get a confidence interval. All right. So the way we do that, we've got one other definition here. Okay? The way we do that, remember we're starting with a point estimate, right? So just picking one number to be our starting place. And then we need to go some amount above that and some amount below that to get our interval. Okay? So like maybe you think, if you're guessing somebody's age, maybe you think they're 27, and then you say, well, I think they're between 25 and 30. And so that kind of tells you how far out to go. And we're going to do the same thing, and how far out from the point estimate we go on either side, okay, is called our margin of error. Okay? Or sometimes you'll see it called the maximum error of estimate. Okay? And our symbol for margin of error is a capital E, a uppercase E. Okay, so that's how far away from our point estimate our interval will cover. Okay. So what we're going to do, we start with a point estimate, and we've already talked about how to get that. Our point estimate is going to be a sample mean when we're trying to estimate a population mean. Okay. And then we'll have a margin of error that tells us how far out from that point, how far out from that number we need to go with our interval. And how far out we go is going to depend on how confident we want to be in our estimate. So in practice, that's all there is to a confidence interval. We've got to sort out some of the details on exactly how we do all that. But the idea, we just start with a point estimate, and then depending on how confident we want to be, we go out some certain distance that we call margin of error. Okay. That's the basic idea, the big picture of what we're doing here. Okay. All right, so the way these intervals are going to look and the way we get there, okay, that in this section, okay, all of our problems we're estimating population means, so our point estimate in this section is always going to be a sample mean, okay, X bar. So we take the sample mean, and once we know a margin of error, we add the margin of error to our sample mean to get the upper limit on our estimate, and we subtract the margin of error to get the lower limit on our estimate. And you can write them as an inequality. Okay? You don't see that very often. Most of the time you see it written like an interval on the number line in parentheses. Yeah. Okay. So most of the way we're going to do these is in this form. And in Hawks, it's even a little bit different. Hawks will just ask you for the two numbers. So it'll call this number the lower endpoint and this number the upper endpoint. Okay. Yeah, because this number will be smaller because we're subtracting, and this number will be bigger because we're adding something to it. So yeah. Yep, you get it. You get it. Good question. Okay. All right, so let's focus on this part. Okay, so on this part, we need a sample mean and we need a margin of error, if we have those two numbers, then we just do this thing. We add the margin of error one time, subtract the margin of error one time, and that gives us the endpoints of our interval. Okay. So let's see what that part looks like with numbers. I'm going to do one of those. Let's look at this problem. Okay. All right, this one says a college student researching study habits collects data from a random sample of 250 college students on her campus and calculates that the sample mean is 15.7 hours per week. So we're saying that the mean amount of time that people in this sample study is 15.7 hours per week. Okay. If the margin of error for her data using a 95% level of confidence is 0.6 hours, construct a 95% confidence interval for her data. Okay. So this problem gives us the two numbers we need to make our interval. Okay. So it gives us the sample mean, 15.7, and it gives us the margin of error, 0.6. So since we have those two numbers given to us, all we have to do is add and subtract, right? We're just going to use that idea. Okay. So we've got two little calculations to do here. So we need to do, well, already forgot, my short-term memory is going 15.7 and 0.6. So this is our sample mean. This is our margin of error. So we need to add these two numbers to get the top value in our estimate, okay, or the upper endpoint's what Hawks calls it. Okay. So there we got 16.3. And then we'll subtract these two numbers. Subtract the margin of error from the sample mean to get the lower limit or lower boundary, lower endpoint, whatever you want to call it, of our interval estimate. Okay. And then if we want to make it look like an interval, okay, on the lower end, our estimate goes all the way down to 15.1, and then it goes up to 16.3. So there's our confidence interval. Okay. So once we get the sample mean and the margin of error, it's easy, right? We add one time, we subtract one time, and we've got our endpoints, so there's our interval. Okay. So let's talk about what this is telling us. Okay. Because even if you don't have to make these things, at some point you'll run into these and you want to know what they're telling you. Okay. So when you look back at our confidence, it says this margin of error goes with 95% confidence. So you don't have to write it out to the side, but I kind of like having my confidence level there so I know what I'm looking at. So this is telling us that we are 95% confident, okay, that the mean or the average number of hours students on this campus study per week is somewhere between 15.1 and 16.3 hours per week. Okay. That was our data. We were collecting how many hours per week did the student study. Okay. So we're 95% confident that it's somewhere between 15.1 and 16.3 hours. Okay. Questions on the interpretation there? Okay. And there is a little bit of subtlety to the exact meaning of interpreting this. The idea here, let me say this. The common misconception, okay, is since we have 95% confidence, you'll see this misinterpreted. You'll see people say there's a 95% chance that the actual mean is between 15.1 and 16.3. That's not exactly true. Okay, it is kind of a ticky-tacky thing here. That's not true because whatever the actual population mean is, it's either in this range or it's not. Okay, so it's either 100% in here or 0% in here. So what this 95% tells us is if we did this process over and over and over, right? So like we collected a sample of 250 students, figured out the sample mean, and then made the interval. We did another sample of 250, made the interval. Did another sample of 250, made the interval. Okay. So we do this process over and over and over. What this number is telling us is that 95% of the confidence intervals we made would have the actual population mean somewhere in the estimate. Okay. So there's like a 5% of the intervals we made would miss. Okay. But 95% of these things will have the real number in that range of values. Okay. That might sound the same, but technically a little bit different there. Okay. All right, questions on that part of the process? That part, once you get to where you have the point estimate and the margin of error, these are easy peasy. You can just add one time, subtract one time. Okay. No questions? Okay. So that leaves us with one piece of the puzzle. Okay. The only thing we haven't talked about so far is how we come up with E, how we come up with the margin of error. Okay. We have said it's going to be based on how confident we want to be. So if you change the confidence, it's going to change this number. It's going to change E. Okay, so we know it's based on the confidence some way, but we need to talk about the rest of the process there. Okay. Before we can do that, and we have a little bit of an idea we need to talk about so we can understand what the formula for E is saying. Okay. Well, let's look at the formula and then we'll backtrack and talk about that. Okay. So here's a formula for margin of error. Okay. This thing's the thing we need to talk about what the heck it is. Okay. So it's this Z looking thing times the population standard deviation divided by the square root of our sample size. So this part's easy, we're just dividing. This part's easy, we're just multiplying, we just got to know what this thing is. So let's back up and talk about what that Z thing is. Okay. So that Z thing, since it's a Z, that should tip you off that it has something to do with the normal distribution curve, okay, the standard normal distribution. It does. Okay. So here, it doesn't show up good on the slide, but what this thing is, it's with the Z's. Okay. The top part is the Greek letter alpha. Okay. And then it's just divided by 2. Okay. So when I write them, I'll have Z with the alpha divided by 2. Okay. And the alpha divided by 2 is down in the subscript. So it makes it look weird sometimes on the slides. Okay. The idea is that we said we were going to have some level of confidence we want. Okay. And that level of confidence sets what these Z values are. We really only care about the positive one. But what's happening is that once we pick a level of confidence we want to use, then that level of confidence tells us the area in the middle of a normal distribution curve. And these two Z values are the Z values that are the boundaries of that middle piece that has that area. Okay? We're about to make a little sketch to help some of that make sense. So the main thing, okay, for right now, is that confidence is area in the middle of the normal curve. Okay. Remember, confidence is the area in the middle, okay, as opposed to the two tails on each side. Okay. And so let's make a little sketch here. In this little sketch, the better you can get what's going on this little picture we're about to draw, the better this will stick, okay, where we're doing these critical Z values. Okay? And the better stuff we do later will make sense. Okay? So the better you can get this picture in your head, the better off you are. Okay? So let's start with a normal distribution curve here. Not great, but we'll work with it. So what we're saying is we've got some Z value over here on the right side, and we're going to label it Z subscript alpha over 2, Z sub alpha over 2. Okay? So the Greek letter alpha is like that. So it's kind of like a fish. And since our curve's symmetric, that means there's another Z value on the other side. That's just the opposite sign, so negative Z sub alpha over 2. And the idea is that the area between these two Z values under the curve is what we're calling confidence. And our symbol for confidence is just a C. That's the area in the middle of our normal distribution curve. Okay. If instead we wanted to talk about the area in the two tails, it has a name also. We're not going to be super concerned with what the name is right now. We'll run into it later. Okay, but if we take the area in the two tails together, both tails together, okay, so this tail, oop, didn't get the color I wanted. So this tail and this tail together, that area we call alpha, which is our symbol for something called significance. Right now we don't care about significance really. We will later, but right now we're focused on the area in the middle, confidence. So if the area in both tails together is alpha and it's symmetric, then how much, so alpha is just some number. So then how much area do we have in each tail? What will we do to figure that out? We just, if we know the area in both tails, but we only want the area in one tail, we divide by 2. So each tail here is alpha over 2. That's where we get this alpha over 2. So alpha over 2. So area in the middle of the curve is our confidence. So when we set a confidence level, that tells us how much area we want to have in the middle of our curve. Okay. Once we figure that out, that sets these two Z values. Okay. And then it also sets significance, which we don't care about yet. And that also sets this alpha over 2, that's area in each tail. So what we're doing, the reason why you see this Z sub alpha over 2, this critical Z value, is once we know how confident we want to be, we say, well, we need to find the Z value that would be the boundary of that area. And that Z value is the Z value that has an area of alpha over 2 to its right. Okay? That's all a critical Z value is. So we pick a confidence level. Based off that confidence level, we know how much area should be in this tail over here. So we say what Z value has that area to its right, and that's our critical Z value we're going to use. Okay? So let's put some numbers on this one and see if it'll help. Okay? So let's say we want to be 90% confident. Okay? So if 90% of our area is in the middle of the curve, how much is left over in the two tails together? 10%, so our significance here would be 10%. So in each tail, if both tails together are 10%, each tail would be how much? 5%. Or 0.05. So if we wanted to be 90% confident, we would say what z-value has an area of 0.05 to its right. That z-value, we just looked that up, that's a chapter 6 problem. That z-value is our, what we call our critical z-value. Okay? That's it. That's it. We're not gonna have to work that hard to find these most of the time right now. Okay? So good news there. All right, but that's what's going on. Okay? It's just based off our confidence, we figure out how much area should be in the tail, look up that z-value to get our critical z. Okay? So nothing too scary once you have an idea of what's going on. Okay? So let's look back at that formula again. Okay? So this thing we find based on how confident we want to be with our interval. And it's just some z-value off the standard normal distribution. This is just the population standard deviation that we're assuming we know right now, so it has to be given to us in the problem. And then n is just the sample size. So we just take the z times the standard deviation divided by the square root of the sample size, we'll get our margin of error. Okay. But, and we're not haven't mentioned it yet, but this is only legitimate if the central limit theorem's in effect here. So we need a sample size of at least 30, or we could be told that our population data is normally distributed. Okay. So we need one of those two things. If we know one of those two things, then we can use this formula to calculate margin of error. Okay. Okay. And then last thing I said, we don't have to work that hard to find critical z's. Most of the time, we don't want to be some weird number, some weird percentage confident. If you're trying to estimate a value, you normally don't decide that you want to be 37% confident in your estimate. Usually we have certain numbers we want to be, like we want to be 90% confident, or we want to be 99% confident, or maybe 95% confident. Right? There's only certain values we typically use, so we got a little, what I call a little cheater table. Okay. Keeps us from having to look up these z-values over and over again. Okay, so this table is also on the bottom of side B of the normal distribution table, and it's got our picture again. All right, so all that's going on, if we just look at our confidence level. So if we want to be 90% confident, our critical z-value is 1.645. Okay. If we want to be 99% confident, our critical z-value would be 2.575. So unless we have some weird confidence level we're trying to do, this table will take care of it. All right. Questions so far? Hanging in there? The main thing today is try to get the big picture. Okay, the calculation part's not hard. What you want to do is get the big picture of what we're doing. Okay? That we're using a point estimate and expanding that to an interval estimate using this margin of error. Okay? That's the big idea. Okay, so let's use our formula. Let's practice using it. It's not bad. Okay, let's look at one. Oh, yeah, we'll come back to that. Okay. All right, so this one says researchers want to estimate the mean monthly electricity bill in a large urban area using a simple random sample of 100 households. Assume that the population standard deviation is known to be $15.50. Find the margin of error for a 99% confidence interval. Okay. So on this one, it just says find the margin of error. We don't actually have to make the interval. So we're just using this formula. So critical z times sigma divided by square root of n. Okay. So sigma and n are just directly given to us. Okay. It says assume the population standard deviation is known to be $15.50. So that's sigma. N is our sample size. So we had 100 households in our sample. So 100 is N. So the only piece we're missing is that critical Z. So do you remember what determines our critical Z? What information we need to look it up? Yeah, we got to have our confidence. Right? So we have to figure out how confident we want to be. So here we want to be 99% confident. So that will give us our critical Z. Right? That 99% confidence. If we were doing it the long way, that sets the area in the middle of the curve. That tells us how much is left over in the two tails. We would find what Z value has that area to its right, and that would be our critical Z. But we don't have to do all that. We can just go back to here. Okay. So we wanted to be 99% confident on this one. So what's our critical Z value going to be? Yeah, so 2.575. Okay. That's it, 2.575. So critical Z, 2.575. Okay. So if you can get all those numbers, two of them just given to us in the problem, the Z we look up based on confidence level, then we can get margin of error. It's no big deal. So margin of error here, just plugging in all my numbers. So E is 2.575 times my standard deviation, which was $15.50, divided by the square root of my sample size, which was 100. And that will give us our margin of error here. On this one, our units we're dealing with money, and we're working out to cents. Okay? So we can take our margin of error and just round it to the nearest cent. Okay? So in my calculator, I got 2.575 times 15.5 divided by the square root of 100. Okay? So here I get 3.99125. Since we're dealing with money, we can round that to $3.99. That would be our margin of error. That's all this one asks for. So we're done on that one. In general, this one we got to cheat a little bit because we were dealing with money, so we got to round our margin of error to the nearest cent. In general, that's not the case. We don't want to round off the margin of error too much. Okay? Because what happens if you have a multi-step calculation, if you round at every step, then by the time you get to the end, your answer's off. Okay? That's what we call rounding error. Right? So what we want to do, this is generally not our final calculation. Right? Because generally from here, we want to add it and subtract it from the point estimate. Right? So we want to leave several decimal places here. In general, our textbook gives you a rule of thumb. It's a little bit of overkill most of the time. Our textbook says to leave at least 6 decimal places. Usually the problems we do in this class, 6 is more than you need. Okay? But if you leave 6 decimal places, you'll be safe. You won't have to worry about rounding error ever. Okay? 4, 5, if you want to be extra cautious, is usually good. Okay? But 6 is our textbook suggestion. Okay? And then we'll do our rounding at the very end, okay, after we actually make our interval. All right. You ready to do the whole thing, whole process? We've done 2 pieces of a 3-step process already. When we kind of started backward, we did the last step where we add and subtract, and then now we've backed up 1 step where we calculate the margin of error. Okay. So almost done everything. So let's put it all together. They're not bad once you get in the swing of things here. Let's see. So let's look at this one. It says to estimate the number of calls to expect at a new mental health hotline, volunteers contact a random sample of 35 similar hotlines across the nation and find that the sample mean is 42 calls per month. We want to construct a 95% confidence interval for the mean number of calls per month. Assume that the population standard deviation is known to be 6.5 calls per month. Okay. So getting started on these, okay. Step one, we need to figure out the point estimate we're using. Okay. Since we're dealing with means here, trying to estimate a population mean, our point estimate is going to be a sample mean. Okay. So what's our sample mean on this one? Yeah, 42 calls per month. It says the collected data and the sample mean here, 42 calls per month, so that's X bar. Okay. So I'm going to put that down. Step one, X bar, 42 calls per month. Okay. So now we've got our point estimate. That's our starting place. Oops, sorry. Step two, we need to figure out our margin of error. We have a formula for that. So we want to figure out our margin of error. So we look at our margin of error formula. We need three numbers for that. We need critical Z, we need population standard deviation, and we need sample size. So let's see what we can find. If we start at the top, it says volunteers contacted a random sample of 35 similar hotlines. So that's my sample size. And then it tells us about the sample mean, which we've already used. Construct a 95% confidence interval. So confidence, what's that going to let us figure out? That Z thing, the critical Z. Okay. So if we want to be 95% confident, we can go down to the bottom of table B. 95% confident, what's our critical Z going to be? 1.96. Okay, 1.96. So our critical Z here is going to be 1.96 based off of our confidence level. And then it says assume the population standard deviation is known to be 6.5, so that's sigma. That's everything we need to do our margin of error calculation. Okay. So go here to step two, maybe. Step two, we calculate our margin of error. Okay. So it was 1.96 was our critical Z, times 6.5 was our population standard deviation, divided by the square root of 35. Going to give us margin of error. We don't want rounding error, so here we want to leave several decimal places. Let's see, we get 1.96 times 6.5 divided by square root of 35. And so here I'll go ahead and leave 6 because that's what the textbook says. So 2.15343. If you round to 6 places, that's what you get. If you're fine probably leaving 4 or 5 on this one. That's 6. That's step 2. That's my margin of error. So then step 3 is the easy peasy one. We just add and subtract. So step 3, we're using this idea to make our interval. It's X bar minus E and X bar plus E. Okay. So my sample mean was 42 calls per month. I'm going to do that plus 2.153453. And we're going to round, and we need to talk about how to round here. It didn't tell us how to round. On Hawks, it will always tell you the number of decimal places to round to. And but if it doesn't tell you our rule of thumb, I skipped over it a second ago. Our rule of thumb says if it gives us the sample data, we round to one more decimal place than we had in our sample data. Most of the time, that's not going to be the case for us. So the bottom one's the one we're going to use. It says round to the same number of decimal places as given in the standard deviation or variance, some statistic, or it should be the same thing as the sample mean. So here we had 1 decimal place in the standard deviation or 1 decimal place in the sample mean. So we're going to round our final answer to 1 decimal place here. So 42 minus 2.153453 gives us 39.846, so that'll be 39.8. Oh, I did minus. Sorry. I did minus first for some reason. So 42 plus 2.153453. Thanks for pointing that out. So this one we get 44.15, and so that'll round up to 44.2. The other one we do minus. On that one, yeah, we get 39.8. Okay, so those are our 2 endpoints. If you want to write it like an interval, you can, but Hawks is just going to ask you for the 2 endpoints. That would be our interval, 39.8 to 44.2. So we were, how confident were we on this? 95% confident that the mean or average number of calls to mental health hotlines between 39.8 44.2 calls per month. So why do we care? Why do we want this kind of information? Well, okay, so on this one it said they're starting a new mental health hotline. So you need to know how many people to hire for staff, right? You know how many people you need to take telephone calls. So your choices are either, if you want to be sure, either you contact every mental health hotline and then figure out the average, okay, so you can cover that, or here we just collected a sample instead, right? So we just had a sample of how many, 35? Okay. And then we use that information to figure out the average for all of them, or the range that the average falls into for all of them. Okay. Questions on any step on that one? Not bad, and the better you get these problems down in this section, I mean, if you get real comfortable with these, then 8.3 and 8.4 are both really easy sections because it's the same big idea. It's just we just have some little adjustments. So the better you get a hold of 8.1, the better off you are for the whole chapter. All right, let's do another one. All right. This one says we've got a large greenhouse production that wants to estimate the average number of days it takes for a hydrangea seed to germinate. Okay, for a randomly selected sample of 125 seeds, the sample mean is found to be 13.9 days. Assuming a standard deviation of 1.4, that would be 1.4 days, right? That's always the same units as our mean. Create a 90% confidence interval for the average number of days it takes for all hydrangea seeds to germinate. Okay. This would be important if you were running a farm here, a greenhouse. Right? You want to know when you need to start the seeds in order to get them in the ground at a certain time of the year. We don't want to have to test every seed. So instead, we've just got a sample, and we're going to estimate the mean. So step 1, and we want our point estimate. Since we're dealing with means, our point estimate, our starting place, is going to be a sample mean What's our sample mean on this one? Yeah, 13.9 days. So there's our sample mean X bar. Okay, so get it out of the way. So step one, we've got our point estimate. Great, now I froze it up. Give me 1 second. For some reason, when I accidentally zoom, it freezes up. Sometimes. Okay, so 13.9 days. There's our point estimate. Step two, we need margin of error. So we need 3 numbers for that. We need a critical Z, we need population standard deviation, and we need sample size. Okay. So as we read through the problem here, it says for a randomly selected sample of 125 seeds, so that's our sample size N. The sample mean is found to be blah, 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 we already got that. Assuming a standard deviation of 1.4, so that's sigma. So the only thing we're missing now is our critical Z. To get our critical Z, we look at the confidence level, so we want to be 90% confident. That's going to tell us about Z. If we want to be 90% confident, what's our critical Z going to be? 1.645 off of the little table. Yeah. Okay. So we're ready to calculate our margin of error. Okay, so step 2 here. E 1.645 times our standard deviation, which was 1.4, divided by the square root of our sample size, which was 125. Okay. And we don't want rounding error, so we're going to leave several decimal places here. So here I get 0.205987, what it rounds to. So the good thing here is if you leave enough decimal places, it's okay if you make a mistake rounding that last digit because it's not going to matter. So that's a kind of another safety valve there of leaving several decimal places. Okay, so there's margin of error. Step 3, I'm just putting these two together, and I've got my sample mean, I got margin of error. So step 3, we make our interval. All right, so sample mean was 13.9. Margin of error was 0.205987. So we'll add this one time and subtract it one time, and we'll be done. So let's see. And on this one, we'll match the mean, so we'll round to 1 decimal place for our final answer. 13.9 plus 0.205987. That rounds to 14.1. And then 13.9 minus 0.205987 rounds to 13.7. And if we want to make it into an interval, we can. 13.7 goes on the bottom. 14.1 goes on the top. Okay. Hawks, all it'll ask for the lower endpoint. That's this one. Upper endpoint, that one. So we are, how confident? We are 90% confident. Yes. Yeah, I will test, and Hawks always tells you to. Yeah. Just these don't. So if you don't have a specification, you just match the mean or match the standard deviation. Yeah, well. So we are 90% confident that the mean or average time it takes for whatever kind of seed this was to germinate between 13.7, 14.1 days. So in practical terms, 14.
On the test, will we?
Yeah, you have these tables, so yeah. And in Hawks, let's look real quick. In Hawks, let me show you where they're at. Because it's not right on the normal tables used in chapter 6. It's its own separate little thing for these critical Z's. So if you go to the tables in Hawks, it's under the standard normal table still, but it gives you all these choices once you click on the standard normal table, and it's the very bottom and it says critical. So if you click on it, then it pops up that same table. And it gives you, it's the last one, Z alpha over 2. And it gives you plus or minus. For confidence intervals, we don't care about the minus. We just want positive. It'll always be a positive critical Z with a confidence interval. They should be the same. In Hawks, it'll always tell you how many decimal places, so you don't have to worry about it. Yeah, so let's see, like on this one, yeah, it says round to 2 decimal places on this one. So. Yeah, we're just worried about the rule of thumb right now because in the slides, those problems don't tell us. But most of the time, it'll be specified for you, so don't have to worry about it. Okay. Other questions on that one? Okay. Yeah, I think I got one more for us. Yeah, let's do one more. Okay. So these, after you've got the process down, these don't take long. And so we'll zip through this one a little quicker. Okay. All right, so this one says the owners of a local company that produce hand knitted hats want to know the average head circumference for adults in their area. Okay. If you want to know what sizes to make, they collect data from 431 randomly selected adults. The sample mean is found to be 24.3 inches. You know, that was an interesting study. Hey, can I measure your head? Construct a 95% confidence interval for the mean head circumference of an adult in the company's area. Assume the owners know that the population standard deviation is 0.36 inches. Okay. So, what do we know here? We know the sample mean is 24.3. That's my step 1. Okay. Step 2, I know sample size is 431. And it gives me at the end, my population standard deviation is 0.36. I also need a critical Z, so 95% confidence. If I go to my little mini table, my critical Z is 1.96. So I can find my margin of error. So 1.96 times the standard deviation, which was 0.36, divided by the square root of the sample size, which was 431. Okay. Gonna leave several decimal places here. On this one, I'm gonna leave 6 places, so I get 0.033988. And to get my final answer, we just add and subtract the sample mean and the margin of error. So my sample mean was 24.3 inches. Margin of error, 0.033988. So let's see what we get. So on this one, we'll round to 1 decimal place. So 24.3. Didn't change much, did it? Because our margin of error was really small. And this one rounds up to 24.3 also, so a little weird. But it's because our margin of error was so small on this one. So in real life, if we got that, we would keep another decimal place because then you have a little bit of idea what's going on. But also in real life, we got that. How confident were we on this? We were 95% confident. So what this would mean if you were in the knitted hat making business in this area, okay, is that you have a really tight estimate, right? Like the mean, the average for the area, okay, is really close to 24.3, right? So you can be confident that if you make a bunch of hats around 24.3 inches in circumference, you're in good shape. Okay, it's going to fit the people around there. So, especially on this one, okay, sometimes going through this trouble of making the confidence interval looks pointless, okay, right? Because we ended up with 20. Our sample mean was 24.3, and our interval looks like 24.3 to 24.3. Okay, so that looks dumb, right? Like we wasted our time, but it's not. This is what we want to happen. Okay. Because now we have a really tight estimate on our population mean. What's useless, okay, is like if we made our interval and we said people's heads were between 0 and 60 inches around. Everybody knew that, okay, so that would be pointless. So if you have a really tight interval, that's really good. That's really good. And the reason why we got such a good tight interval on this one compared to some of the other ones we've done, well, we said it was because we had a small margin of error. Why was that? Main thing on this one was we had a pretty big sample size. Okay? The standard deviation was small, we had a pretty big sample size. Okay? So if you want a better, tighter interval, one way to do that is to increase the sample size. Okay? So it boils down to everything else we do in stats, just about the bigger the sample, the better. Okay? Bigger the sample, the better. All right. Questions here? All right, one last thing. You don't have to calculate anything on this one. Okay? This is an interpretation problem. Okay, something to think about here. This is pretty interesting. So let's take a look here. This one says we got a new study that compared the sensitivity of HIV home test to that of professionally administered tests that use the same testing procedure. Okay. Measures of test sensitivity represent the percentages of results that are correctly labeled positive when HIV is actually present. So sensitivity rate is the true positive rate. If you have the disease, you actually test positive. Okay. And then we got a table that gives us the 95% confidence intervals for the sensitivity of the home test versus the professional test. So here they are. Okay. So the home test, our estimate on the sensitivity there, okay, 95% confidence between 86.6 and 96.9%. Professional test between 95.85% and 99.08%. Okay. So it's multiple choice. I'll give you 3 choices on how you interpret this thing. Okay. Let's look. So choice number 1 says, so we're just interpreting here. Okay. Choice number 1 says the professional tests were found to be far more reliable because it had a 99.08% sensitivity. The home test only had 86.6% sensitivity. So there's confidence intervals again. Okay. Choice number 2 says home testing methods for HIV are just as sensitive as those administered professionally. In fact, they're even more sensitive since they have a possible 96.9% sensitivity compared with a possible 95.85% rating for the professional test. So the first one, what does it do? The first one says, this one's better because this end is bigger than that end. The second one says, this one's better because this end's bigger than that end. Okay. And then number 3 says the results provide reasonable assurance that the home test is as effective as the professional test. I think 3. All right, we're going to take a vote. Okay. Everybody got a choice? Who thinks number 1, professional test, is better? Nobody? Who thinks number 2, I got one. All right, so who thinks number 2, the home test, is better? Who thinks number 3, they're the same? I think I got some no votes in there. Number 1? Taking a repoll. Number 1? Number 2? Number 3? Okay. All right, so here's the idea, okay? Number 3 is our best interpretation, okay, that they're as effective as each other, okay? So why? So let's think about, all right, let's, I'm gonna kind of put that one on the fake number line using red. I'm gonna put the professional test on the fake number line using blue, maybe. Get out of my way, all right. So if this is our number line, what do they look like when we put them both on the number line? So here red would be like somewhere in there. But on blue, what happens? The 95.85, that's like down here, right? So if we plot both of these intervals on the number line, what happens? They overlap. So what's possible, right? Remember, this is just an estimate, right? We're saying the real mean somewhere in here, the real mean somewhere in here. So what's possible is that the real mean for both of them is in both intervals, right? It could be in both intervals. So you might think, okay, the intervals overlap. Let's adjust them. Let's like move the ends where they don't overlap anymore. And then we could say, for sure, if we could do that, if we could move the end of the blue one over here, move the end of the red one over there where they're not overlapping anymore, we could say for sure the blue one's better, right? Because it would have higher numbers. Yes. So here's the idea. If we want to be more confident, our interval gets wider. Our interval gets wider. So the only way we could make the intervals not overlap, this is very good to pick up on. The only way we could make the intervals not overlap is to be less confident. And who wants to be less confident about HIV test? Okay? Nobody. Okay? So actually, the more confident we were, so like if we change these to 99 instead of 95%, they would overlap even more. They would overlap even more. Okay? So, and then the other thing on the other 2 interpretations, why they're so bad, okay? It doesn't make sense to compare the upper endpoint with the lower endpoint, either way. Okay? You would want to compare upper endpoints and lower endpoints if you were thinking about that. So, okay? Questions there? This kind of stuff is especially important right now. Everybody's having to get COVID tested. They work the same way. They have sensitivity rating. You know? So, something about. All right, that's it. It's all 8.1. Okay. If you didn't get on the sign-in sheet, we'll bring it up front. You can get on there.